let us recall how we can distribute electrons in the various orbitals. Some definitions are already given here. So, let us look at the orbital. In the first shell we have s orbital. The number of orbitals, there is only 1. So, the maximum number of electrons can be placed here is 2. And when we go to the second shell, we have s and p orbitals. Here 1 s orbital and 3 p orbitals are there. So, put together 2 electrons from the s orbital and 6 electrons from the p orbital leads to total 8 electrons in the second shell. And when we move to the third shell, we have s p d orbitals, and s orbital can have 2 electrons, p can have total 6 electrons, and d orbital can have total 10 electrons. So, 10 plus 6 plus 2, 18 electrons are possible in the third shell. And when we move to the fourth cell, we also have the f orbitals additionally, which has 7 degenerate orbitals, which can accommodate 14 electrons. So, 18 plus 14, 32 electrons are possible in the fourth shell. As we mentioned earlier, degenerate orbitals are orbital having the same energy. When we talk about ground state electronic configuration, what we mean is the electrons are all in the available orbital with the lowest energy, and when we say excited state electronic configuration, what we mean is the electrons are in the orbitals with the high energy. So, these two terms will be used quite often in the course. Let us look at electronic configuration. So, the first rule we have to follow is the Aufbau principle, which says that the electrons of an atom occupy quantum levels or orbitals starting from the lowest energy level and proceeding to the highest, with each orbital holding a maximum of 2 paired electrons having opposite spins. So, this is what is the Aufbau principle. So, according to this, the electrons are filled. So, the order of filling is given here. First 1s orbital, which is having the lowest energy, will be filled, followed by 2s orbital, which is having little bit higher energy. Then 2p orbitals will be filled, followed by 3s, 3p. After 3p orbital, we do not directly fill the 3d orbital, because 4s orbital is having lower energy than the 3d orbital. So, after filling the 3p orbital, we will move on to the 4s orbital, and then we will fill 3d orbitals. So, after 3d orbital is filled, then we will move on to 4p orbital, then 5s orbital. So, this is how the order of filling is followed according to Aufbau principle. The next one what we follow is Pauli's exclusion principle. So, here no more than 2 electrons can occupy each atomic orbital. The 2 electrons must have opposite spin. The next rule to follow the electronic configuration is Hund's rule of maximum multiplicity. So, basically when we talk about the Hund's rule, we talk about spin states. So, electrons will singly occupy all the available empty orbitals of the same energy before electrons begin to pair up in the same orbital. So, this is what is called Hund's rule of maximum multiplicity. So, when we say singlet configuration, that refers to spin 0. That means, in this particular configuration there is no unpaired electron, all the electrons are paired. And when we say triplet configuration, there is spin level is 1 and there is one unpaired electron. These terms are generally used in atomic chemistry, spectroscopy and quantum chemistry. Let us look at molecular forces. We have intermolecular forces and we have intramolecular forces. When we say intermolecular forces, these forces operate between the molecules, and when we say intramolecular forces, these forces operate within the molecule. Some examples of intermolecular forces include London dispersion, van der Waals force, dipole interaction, hydrogen bonding and Coulombic interactions. These forces are very weak in nature. When we talk about intramolecular forces, that is the forces within the molecule, the examples include covalent and ionic bonds. These are very strong in nature. So, here are some pictorial representation of this inter and intramolecular forces. So, London dispersion happens between 2 different molecules. When we say hydrogen bond, this also happens between 2 different molecules. The distance varies. The London dispersion is pretty long range interaction, whereas hydrogen bonding is a very short range one. And we also have dipole-dipole interactions. Here we have the hydrogen chloride molecule, chlorine is electronegative. So, this pulls the electron towards, this is having a large electron density cloud, and hydrogen is in the nearby molecules is pulled by the electronegative chlorine. So, the dipole-dipole interactions arise. Let us move on to the next one, which is types of bonds. Oh, not this 0-0 bond or not this Fevicol bond. We will be talking about different types of bonds. Some of the types are given here. The ionic bonds, that is present in sodium chloride. Covalent bonds, this is present in many organic compounds. This is based on orbital overlap. Two types of bonds can form, that is sigma bonds and pi bonds. Based on electronegativity also, we can say there are two types of bonds, that is polar and non-polar bonds. We have polar bond present in HCl. Organometallic bond is present in ferrocene, butyl lithium and Grignard reagents. Coordinate or dative bond, which is present in coordination complexes, and we have metallic bond, which is present in metals. The metallic bond is present only in pure metals. Except this metallic bond, all the other type of bonding needs at least one non-metal as the bonding partner. Ionic bonding basically involves transfer of electron between atoms. So, in these kind of cases, one atom loses an electron and the other atom gains that electron. Although in organic chemistry, we say these are covalent compounds, the difference in electronegativity between carbon and other atom is responsible for many organic reactions. So, that is the reason, even though when we say ionic bonding, we do not mean the inorganic ionic bonding like sodium that is present in sodium chloride or similar compounds. In organic compounds, the electronegativity difference between carbon and say halogens or oxygen or nitrogen is mainly responsible for many organic reactions. Carbocations, electrophiles and carbanions or nucleophiles are the two important intermediates involved in many organic reactions. These are the ionic species we will be encountering in this particular course. Although true ionic bond does not exist in polar organic compounds like ketones or carboxylic acids, the charge polarization is the driving force for their reactivity. We will see about these kind of interactions later in this course. Let us recall some of the things we have studied earlier. Ionization energy is the energy required to remove an electron from an atom. The elements with low ionization energies are called as electropositive elements. Some examples include alkali metals. So, lithium, sodium are shown here. These are the electropositive elements, and elements that readily acquire or accept an electron are said to be electronegative. Some examples include fluoride, chloride. So, these are electronegative elements. You are already familiar with core electrons. So, the electrons in the inner shell are called core electrons. Generally, they do not participate in any chemical bonding. And when we say valence electron, these electrons are the outermost shell electrons, and elements in the same column of the periodic table have the same number of valence electrons. They participate in chemical bondings. They determine elements' chemical properties. When we say carbon, silicon and germanium, they have 4 valence electrons. Similarly, nitrogen, phosphorus, arsenic have 5 electrons, oxygen, sulfur, selenium has 6 electrons, and halogens have 7 valence electrons. They participate in chemical bonding. These valence electrons determine elements' chemical properties. Compared to the weight of the proton or neutron, the electrons are 2000 times lighter, yet they are the one. Compared to the weight of the proton or neutron, the electrons are 2000 times lighter, yet they are the one which decides how the reaction occurs. This is because they are present outside the nucleus, and when two atoms or molecules come closer, electrons are the tiny part of the matter that interacts first. Due to this, we focus our attention to electrons when we study organic reaction. be it a lone pair, pi bond or even a sigma bond. Ionic bonds are basically formed when there is a transfer of electrons causing one atom to become positively charged ion and the other to become negatively charged ion. An electropositive element transfers one or more electron to an electronegative element. This is how ionic bonds are formed. In the covalent bonding, bonding occurs due to the sharing of electron between atoms. Nucleus of one atom attracts electrons of the other atom. Electrons of one atom is repelled by electrons of the other atom. The attraction of bonding electrons to the nuclei of the bonded atoms leads to lowering of energy and therefore, the formation of a bond. According to the octet rule, that is the Lewis octet rule, an atom is most stable if its outer shell is either filled or contains 8 electrons and it has no electrons of high energy. Of course, one exception to this rule which we will encounter quite often is the hydrogen. Hydrogen has only 2 electrons. So, except hydrogen, all the second row elements which we will be studying in organic chemistry follow octet rule. Of course, boron is an exception. Covalent bond can be categorized under different categories. One is polar and non-polar covalent bonds or sigma and pi bonds. When we look at polar and non-polar covalent bonds, some examples of non-polar covalent bond includes bonds formed between same atoms, that is between hydrogen, fluorine, chlorine, like that given here. When we talk about polar covalent bond, it is formed between atoms that differ in electronegativity, say for example HCl, water, ammonia, methane, etc. When we talk about sigma and pi bonds, the sigma bonds are formed by axial overlap of atomic orbitals across the internuclear axis, and pi bonds are formed by the sidewise overlap of atomic orbitals.